Hey guys, here's your video of me explaining Le Chatelier's principle. We're not going to do anything super in-depth or super complex with this principle, but you do need to understand how changing different things about reactions are going to shift the equilibrium. So what this principle basically says is, if you do something to a reaction, if you change the concentration of something in it, if you change the temperature of the reaction, or you change the pressure surrounding it, that reaction is going to shift to try to maintain equilibrium or maintain the balance. So think of reactions as Thanos. Basically, they are striving to be in balance at all times. And if anything changes, they're going to try to fix it by either progressing forward or progressing backwards. So in this sample reaction, we have H2CO3, which is in equilibrium with CO2 and H2O. And if you took this reaction, like you had this reaction going in a beaker in front of you, let's pretend. If you add a crap ton more of H2CO3 to that reaction, suddenly you've thrown off the balance of products to reactants. And so to fix it, that reaction is going to progress forward because it's going to try to make more products to compensate for the increase in the reactants that you just threw in. So we like to say that that will shift to the right to form more products, and that compensates for all the extra concentration you've added to the reactant side. If you did the opposite, if you threw in more product, the opposite's going to happen. Your reaction will shift to the left, or the backwards reaction will happen more to encourage the formation of more reactants to balance it out once again. Temperature is another thing that can influence equilibrium or can influence the way a reaction is going to shift. This one's a little bit more complicated than just throwing in more product or throwing in more reactant, because you're not just increasing temperature on the reactants or the product side, you're increasing the temperature overall. So if you increase the temperature overall, the reaction's going to shift in whichever direction absorbs heat. So what that should mean to you is that it's going to shift in the direction that's an endothermic process. Because endothermic reactions need heat in order to occur. They absorb heat in order to progress. So if you're adding heat, you're going to encourage the reaction that absorbs heat to happen. Exothermic reactions give off heat as a product, so you're not going to encourage more exothermic product to form by adding heat. You're encouraging the opposite to happen. So to give you an example here, we have an endothermic example, which is PCl5, which is going to decompose into PCl3 and Cl2. So if you recall, breaking bonds requires an input of energy or an input of heat. So that's absorbing this heat, why the heat is listed as a reactant here. So if you add more heat, you're going to encourage more products to form, causing that shift to the right, because this decomposition is an endothermic process. It would not shift to the left because the formation of PCl5 is an exothermic process, because bonds are forming and therefore that's releasing heat. So you would never encourage this backward reaction to happen by increasing the heat of the reaction overall. Whoops. The exothermic example I have for you is SO2 plus oxygen forming SO3 and heat, because this forward reaction is an exothermic reaction, releasing heat because you have bonds forming between this oxygen and the SO2 to form this compound right here. So if you're increasing the temperature, you're going to encourage the backwards reaction to happen, because the backwards reaction, this decomposition that is happening backwards, is the endothermic process, the process that requires overall breaking of bonds and the overall absorption of heat. So that's how you know that that reaction will shift left to favor the reactants of this particular expression. Pressure is another thing that can influence the equilibrium or the shift in whatever is going on. So the unique thing about pressure, though, is that it only really affects the gaseous particles in any given reaction. So if you're going to decrease the volume of a reaction, you're going to increase the pressure. And the shift is going to be towards whatever side has less gaseous particles. Okay? So to give you an example here, we have our N2, our nitrogen, and our hydrogen, and in the product side, we have our ammonia. Notice, though, that all three of these are in a gaseous state, so you might be going, well, where's the less particles? Like, where am I supposed to shift? But that equilibrium is going to shift towards the right, because I told you it is going to shift in favor of less particles, right? So here we have N2 and we have a bunch of hydrogen. So though all those are separate molecules, like it's going to be H2, 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 N2. So you have 4 different particles right here. Whereas on this side, you only have 2 particles. You only have 2 of your NH3. And if you scale it up to like moles of each, the same fractional ratio occurs in the gaseous state. So really, you have less gaseous particles on the right, even though you have the same amount of atoms. It's just that you have bigger molecules over here than you do over here. So overall, if you increase the pressure, it's going to shift towards the right there. If you were to decrease the pressure, it's going to do the opposite. If you decrease the pressure, it shifts to favor more gaseous particles. This video, I very much encourage you to watch. It's going to give you visual representations for everything that I just said and more. I'm not going to play it on this video explanation for you. You can go and click on it yourself and watch it. But I hope that that was helpful in explaining shifts in equilibrium. Once again, reactions are Thanos. They want to maintain balance. Stay safe. Have a good day.